Okay, welcome back. We got an exciting 2 more sessions, and then we are going to break for lunch. Today, right now, we've got Mostyn from Vewd Software. He's going to talk about Bazel Remote Execution API versus Goma. So let's welcome Mostyn on the stage.
So, hi everybody. Here's my background. I work at Vewd Software, and our main product is a smart SDK aimed at smart TV. And for the past 5 or so years, it's been based on Chromium. Chromium for us is a pretty large code base. I hear from some of the Google guys that it's only medium, but so maybe you got most of the crowd here. I'm guessing it's pretty big for you too. We're only interested in the Linux and Android part of Chromium, and only a subset of that. So that's kind of my bias. This is the scale that I'm building on. We use Clang and GCC in a single build, which is a bit unusual. If we're cross-compiling, sometimes there's multiple versions of GCC and Clang because you have to build Chromium twice to generate snapshots if you're building for a different architecture bitness. So if you're on 64-bit development machine building for 32-bit, you need to build a 32-bit version of Chromium to create this startup data. So that's quite painful for a build the size of Chromium. And we've got several offices around the world. So Chromium is large and it's constantly changing, and this is pretty bad for a build system. Puts a lot of pressure on us. It's painful to build on a workstation, so much that basically nobody ever attempts this anymore, even if you've got a really powerful workstation. It requires bleeding edge Clang, and there's not much we can do about that because the Chromium team at Google is interested in taking new C++ features all the time. It's a mostly hermetic build setup, which is pretty good. It allows us to get reproducible builds, and it helps with our cache hits. And we're stuck using whatever Chromium decides to use for their build system. So this is GN plus Ninja, which sort of looks like Bazel from a distance. And if you're lucky enough to have Goma, this sort of looks like the Bazel Remote Execution API. So Goma and Bazel have both come from Google, and they look very similar. One is probably an ancestor of the other. I assume Goma is older, but I don't really know. I think Goma is used for some other open source Google projects, maybe Android, but I have not played with this myself. And it's injected into the build via a simple compiler wrapper, Goma CC, much like ccache if you've ever used that. So how painful is it to build Chromium? I've got some data here that's a few years old, but the trend has continued. The interesting part here is that the build time increases by about 1% per week, which is pretty scary if you ask me. So here's a graph. This is a couple of years ago from Mac, but the trend holds for Linux as well. To build on a single machine, you're talking multiple hours for a sane workstation for most companies. So just a quick refresher of the C++ build model, since that's the majority of the Chromium build. You first have to pre-process source plus headers plus macros, and you get a large pre-processed source. Then you have to compile that source to produce an object file, which can be slow, and you have to eventually link that with a bunch of other object files when you're done, and that can be very slow. So to build Chromium quickly, what the strategy that's employed is to reuse as much as possible, to distribute as much as possible, and to link locally. And this is the typical setup for most downstream Chromium projects, if you don't have Goma. You can use ccache to get the caching. Unfortunately, it's local only, but when you get a cache hit, it's very fast. And because it's local, your cache hit rate is pretty low. And then to distribute the build, people tend to use icecc or distcc, which sends out the pre-processed source to your network. This only works on a LAN, and it tends to be self-managed. With icc, people enroll their own workstations into the build farm, and this can be pretty unreliable. And the other issue is that you get slightly different warnings from Clang when you're building pre-processed source to building the original sources. In theory, it shouldn't happen, but there's always a Clang bug that causes trouble. And Chromium is built with W error, so warnings are turned into errors, which makes this really annoying. So back in 2013, this is kind of what the frequency distribution of our build times look like. At the low end, we could build in under a minute, but this is a fairly rare occurrence, and up to about 3.5 minutes in the worst case. Fast forward to 2018, it was more like this. So there's two interesting parts about this made-up graph. The first is that the builds have grown to about 10, 11, 12 minutes on average. And there's this second lump over on the edge, which is I'd just come back from drinking my coffee and the build broke because somebody's ICC workstation was overloaded. So this is getting pretty frustrating. And there's nothing we could do because we're sort of hitting inherent limits in the ICC protocol, and ccache is not going to give us any more cache hits than we can already get locally. But then there was this light on the horizon. Early in 2018, the Goma client was open sourced. It supports Linux, Windows, and Mac clients, although we've only been testing it with Linux. I hear that it's experimental on Mac, but I know that the Chromium Edge team has been using their own Goma backend, so Windows must work. It's kind of like distcc pump mode with a centralized ccache. So distcc pump mode works by only uploading the files once, and therefore you remove the Ethernet, the gigabit Ethernet upload ceiling that you can quite easily hit with ICC. So there's a compiler proxy service that runs on the client, kind of like the client that runs when you start Bazel, or the server that runs when you start Bazel on the client machine. There's a Goma CC compiler wrapper that feeds jobs into the compiler proxy. There's a custom preprocessor that's optimized just to find the inputs to a C or C++ compile job, and lots of caching optimizations under the hood. At this point, there was no server available, but it was protobuf over HTTP, so this is something that's quite easy to reverse engineer. And these are the two most interesting messages in the Goma protocols. It's much simpler than a remote execution API. You can request an execution, which uploads the command, hashes of all the inputs. Maybe some of the inputs are included, and the expected outputs. And the response you get back either says, I had these missing files with these hashes, can you upload them please in a second attempt, or here's your results. Inside the Goma client, these are, I think, the few caches that I found this morning when I was double checking my notes. There's an input file cache, so you don't have to keep continuously reread the same header files on every compile unit. There's a directory listing cache, so you don't have to hit performance problems in your file system, particularly on Windows, I think. There's an input dependency cache, which means you don't have to rerun the optimized preprocessor every time you rerun a job. There's a compiler info cache to quickly return details about the compiler, which is included in the hash that's uploaded. And there's an output cache, which is off by default, and when I tried it, it was no faster than using a network cache. On the back end, there's more caching still. Input caching is required to function because if the Goma client guesses wrong and doesn't upload all the required inputs, you get another request. The Goma client will try to just upload the inputs that were missing the last time. If the Goma client was to try and upload all the inputs on every exec then you'd have no better than uploading preprocessed source from a bandwidth point of view. So input caching is not an explicit part of the protocol, but it's required to function. Output caching is completely optional, but gives you a big speed up. And the input caching has different access patterns to the output caching. During a build, common header files can be included thousands of times. I think we have 20 to 30,000 build steps in Chromium. They're not all C++ compile jobs, but a lot of them are. So common headers are included a lot, whereas the output cache is basically cached once per build and returned. And then if you make a rebuild, each output object is returned once during the whole build for the whole package of Chromium. So this is the design we ended up implementing. On the private cloud side, we've got all communication going through a scheduler, which is basically a simple load balancer which sends data, sends the exec recs to the least loaded worker in our cluster. There's a memcached instance that keeps track of all the input files. There's a toolchain server which maintains all the toolchains indexed by their hash. And there's an output cache which is using Bazel Remote. We're actually kind of abusing the Bazel Remote API here, storing arbitrary blobs via the action cache because there's no validation there. Actually, could I just go back one slide? On the Office side, we have some workstations that just connect directly to the scheduler, but also we have, in some offices, we have a pre-cache. So we can do fast cache lookups in the Office LAN. In the case of cache miss, then the pre-cache just forwards to the scheduler and continues as normal. On cache miss, when the request goes to the scheduler, it's serviced by one of the workers and sent back. It's cached on the back end and then sent back to the pre-cache, which is cached there for the next local client to come along. So I call our backend a toy because compared to Google scale, it really is a toy, but it scales pretty well. I aim to have at least Ninja-J 1000 working and keep all the workers busy. And this works pretty well in practice, apart from parts of the build graph where there isn't enough jobs to have running at once. And because the output caching, because the build is mostly hermetic, we get mostly cache hits on rebuild, which means our CI is basically populating the build cache and developers getting 99% cache hits quite frequently. It's usable from offices around the world, but obviously you're dependent on their connection speed to the backend. And I think in most offices we have up to a gigabyte bandwidth, but it's more likely to be half that. So here are the results. You can see that we're not quite as fast as the absolute fastest builds with ccache. We give up maybe 10, 15 seconds. But to get a really high hit rate is really common, so our Goma build times are much less distributed. And the results we see from this are pretty good. Our developers are more willing to experiment with new compiler flags, new tool chains. They're more willing to make device builds and actually test them on device. There's much lower developer frustration. We need to find other things to be annoyed by. And the maintenance has turned out to be really low. So this is all pretty great, but this is a Bazel conference, and I don't know how interested you guys are about Goma. But they're actually quite closely related enough that there's bugs that are basically identical in both backends that I found. Implementation ideas and optimizations can be shared, and the remote execution API working group is really open and much friendlier than the Goma team, which is a bit more hidden within Google. So then earlier this year, there was an open source Goma server released. But it's not really a server, it's a proxy to RBE. And then the Goma team says to me, oh yes, we're considering switching the Goma client to speak RE API. And that kind of had me worried because we would really like not to go back to the bad old days of ccache and icc. So I started thinking about what we could do to avoid that scenario. Could we switch to RBE? We're not unable to because we need to work with GCC and this is not supported by the Goma client. The Goma client has a new feature to upload the toolchain as if it was an input to a compile job. And this only works for Clang at the moment. And to make it worse, it's blocked on an internal Google bug that I can't see the details of. So we're kind of stuck there. But also, my boss wouldn't let me do this anyway. We need to build everything on our own hardware. But there's other open source RBE backends. Could we use one of those? Well, no, because they still don't support GCC either, and it's a bit unproven. I've heard of other companies that work downstream from Chromium having tried this. So far, no public success stories. I'd be really interested to hear if there's anybody here that can prove that wrong, but we'll see. And it's difficult to gauge how how performant this would be without actually having a full-scale test run. On the other hand, maybe we could add REAPI support to our Goma backend. It's a similar high-level design. We're already using Bazel Remote. Could we basically get there piece by piece and test with Bazel to get remote caching up and running, and rec to test our remote execution implementation? And this is the design that I've come up with. So we have all the same components. The only difference here is that we've opened up connection directly to Bazel Remote from the client side. And we have to add REAPI endpoints to our scheduler and to our workers. So far I've made progress on the Bazel Remote Cache API. And I can build large projects using remote caching with Bazel Remote. Tested with Bazel and also with rec. I've added basic Clang support to rec since we need that to work to build Chromium, which is going to be my test case. And I haven't tested building all of Chromium, but I can build a useful subset. So I have a prototype REAPI execution service. This is just enough to successfully build with a few bugs, but if I rebuild enough times, I can populate the cache. I'm still learning this part of the API, but it's much smaller than the cache API, so I'll get there soon. And I've made rec request inline results, so I can then move on to an experiment. Later on, I will have to integrate all of this with our working Goma backend and optimize and so on. And there's a few other things like figuring out a way how we can use a multi-tool chain, use rec with different tool chains in a single build. Since rec is, I think you specify some environment variables which are related to the tool chain that you're uploading. We need to figure out a wrapper script to make this work. So here's our experiment. If we can build Chromium and then rebuild, if we can build Chromium with rec and Bazel Remote to populate the cache, how fast can we rebuild? It's not really worth considering the incremental rebuild time because this is dominated by the running Ninja, which takes a couple of seconds, and then linking after the result. So that's not really worth measuring. And these are our initial numbers. To do a hot cache rebuild with rec is a bit under 4 minutes. Although this seems a bit high, so I'm not too confident in these numbers just yet, compared to about a minute with Goma. And while we're doing this experiment, the client-side CPU is about 100% on the rec build. So something seems a bit off here, but I haven't been able to narrow this down yet. And there's no speed up above 1 thread per core on my client, whereas with ccache you can run hundreds. So digging into things a bit, here's what I've got so far. For a single execution of rec, it's actually faster than Goma, but it takes a lot more user and system time. So this is time spent in the process doing work and time spent in kernel space doing work for the task. Whereas Goma is pretty idle. It must be waiting around for some stuff. Rec has some metrics that are kind of deciphered. It seems like the bulk is in the compiler depths and building the Merkle tree and calculating the digests. These are all things that are cached in the Goma client. And looking at Goma, we can basically see this. The RPC wait time is the bulk of the time here, and everything else it does locally is a pittance in comparison. So I think this is the problem I'm hitting with rec. It takes way more local CPU resources than Goma, and this is probably the bottleneck I'm hitting. And while Goma's RPC call is slower, it's not that much slower, and it's also doing more work on the server side than on the client side. There's also differences in the protocol. It's using Proto 2 versus Proto 3 in REAPI, and it's HTTP1 instead of HTTP2. I haven't dug into these yet, but we'll see if that makes much of a difference later on. A couple of other things I noticed with rec is that if you specify your endpoints by domain name, it spends a lot of time just doing DNS lookups. This is something that maybe we could put a warning in rec for. Rec is basically single fire. For every single compile job, you run rec once, it does some stuff, and then exits. So if you're using a domain name here, then you have one domain name lookup for every compile step in your build graph. And there's no good way to handle extra inputs yet. Rec figures out the inputs to a job by basically running the compiler with -m to generate a makefile rule with all the header dependencies. But this doesn't cover things that aren't source dependencies like Clang plugins or files specified on the command line. So this tells us that at first I was scared that the Goma client would be switched to talk REAPI, but now it sounds really good. If I can get our backend to talk the required protocols, it would have really fast, cheap pre-processing, it would have really fast cache lookup. It's got quite a wide language support, so besides C and C++, it's got Rust, Java, and Dart, and it's extensible to more languages if you're willing to hack the Goma client itself. And it's easy to drop into other build systems, so this is pretty cool, in my opinion. So what have I learned along the way? Well, first of all, I learned that cache optimization is really difficult. In the Goma build, there's this inherent separation between input files and output files. And since we're only dealing with compiler jobs with Goma, this is fine. The output of a compiler is never used as the input for a compiler if you're discounting linking. On the other hand, REAPI is more general, and maybe that's more extensible in the future, but it's not something I can use at the moment. And since I can't easily distinguish between inputs and outputs, I basically have to put them all in a single storage form. And due to the size of the Chromium codebase, this means I have to store them all on disk at the moment. I have some ideas for possibly optimizing that, but haven't had time to check yet. One of these things is we could try to do different caching behavior depending on the source of the uploader. So if we can tell the difference between the client side and the backend side, maybe we know that inputs are only uploaded from the client side, so we put them in memory. We know that outputs are only uploaded from the backend side, so we put them on disk. And there's a few corner cases that we can decide to do either. And this could potentially work if we're only interested in a compile service. If our Goma backend doesn't need to be a general, or our Goma/REAPI backend doesn't need to be a general service, then maybe this is OK. On the other hand, maybe we could just add a fancier cache. We could have tiering. We could have LFU cache where we put the most frequently used in RAM as well as on disk. We'll see. Another thing I noticed is that inlining of results is optional in REAPI. This seems kind of weird to me. If you're going to do a round trip to check the cache results and the cache results aren't huge, I think they should just be returned along with the answer if it's in the cache or not. In terms of Goma, there's basically a single round trip for a cache hit. On the REAPI side, you basically have to check a whole bunch of things. Even in the case of a cache hit, you need to check if the results are inlined, and they're not allowed to be inlined unless the client requested it in the first place, which is fine, but I think the default should probably be flipped. And that's basically it. I think this is a really cool technology that's really easy to drop in to build systems without having to switch everything to Bazel. I'd like to hear from anybody who's attempted this with Rec or Goma, or in particular the Goma server. And there you have it. Any questions?
I have to say I was particularly interested in this talk. I think there's a lot of great questions in there, and I think there'll probably be some questions in the audience. I was hoping, anybody? Igor? No? Okay. I'll give folks a few seconds to think about this, because I work directly with the Goma team.
Okay.
And work directly with.
Complain to you afterwards.
Well, you just did.
Okay.
And I work directly with the Bazel team and the remote execution team. So, you know, this is a timely talk and a good discussion. We have a question up in the balcony.
Hello, thanks for the talk. I wrote down lots of things with stars next to them. Especially, I really liked mentioning when the Goma build starts, it doesn't necessarily load all of the input files for compile unless they're needed. I thought that was an interesting point that I'd like to maybe elaborate more on.
Yeah, so the Goma client has heuristics for deciding what it should upload. I don't know all the details, except I think it, because it runs a server that runs during the entire build, it can remember things, header files that it's uploaded previously. I think the heuristics try to pick out, oh, this is the main source file for the build, so that we should probably upload that. And in the case of it guesses wrong, it's just one more round trip with missing results.
I also like the comparison of whether inlining is optional with the REAPI and kind of the steps required for that. That was really effective. So yeah. I'd love to talk to you after this.
Great. Nope.
I was trying to get one of the remote execution API team members to stand up and say something, but so far, no luck. Yeah.
It's okay. I've seen them around.
Yeah. Certainly.
I haven't seen anyone from the Goma team here. You should.
They're not local, so
no.
That's part of the reason. So we can certainly chat with them. Let's talk offline a little bit about this, and let's give a. Oh, we have another question.
Yes.
Okay.
A separate one, I swear. One thing you mentioned that I thought was interesting was, for example, when you build things in C or C++, you have to expand all these, transitive includes. Is that something that is cached, as in the contents of that preprocessor expansion? I know that you mentioned that there's a special header parser for dependencies, but is the content of those files cached at all, or is it still?
There is a separate cache for the content of the header files. I think there's also a separate cache for the results of the custom preprocessor, so sometimes you don't even need to call that preprocessor. And the preprocessor is optimized. It's not a real preprocessor. It just tells you the inputs. So it doesn't process all the file data.
Oh, thank you so much. That's fantastic.
Oh, one other thing, there's a Clang project, I think Clang scan depths, which tries to implement some of the same optimizations for Clang, but I'm not sure. I haven't tried that in practice. I only found out about that yesterday.
That's very interesting, because that's something I wouldn't have to implement myself for pants. So yeah, I'll look at that. Thank you very much.
Actually, in the Goma client, maybe even the preprocessor is a separate binary that you could try running.
Awesome.
I think it's BSD license code. It's quite nice.
Wonderful. Thank you.
Okay. All right. Thank Mostyn.
Thank you.
Thanks. I appreciate it.